Our next speaker is, can you pronounce your name? Because I won't do it correctly.
Qinghai Zhong.
Qinghai Zhong. Excellent. From Graz, Austria, who will speak on zero-sum sequences. Please.
Thank you. Today I'll talk about monoids of weighted zero-sum sequences. This is a joint work with Goldinger and Davenport. The talk will divide three parts. First, we will give the definitions of weighted zero-sum sequences. Then we'll talk about the algebraic properties and arithmetic properties of monoid of weighted zero-sum sequences. First, we see sequences over a finite abelian group. The let G be an additive written abelian group. Let G0 be non-empty subset. By a sequence over G0, we mean there's a finite onward sequence with terms from G0 and repetition of terms not. Or you can see it as a multiset with elements taken from G0, or you can view it as an element of the free abelian monoid, the free abelian monoid Fg0 with basis G0, where the operation is a concatenation of sequences. Then a sequence over G0 is also a sequence over G. Usually we can denote S. That's from the G1, G2 up to GL. Also can reorder it, and it's G2, G1, G3 up to GL, since the order is not important. Then we see that here we can read is a product of G to the power VGS. Here the VGS, we see it is a multiplicity of G in S. And the length of S is L, or the sum of VGS. It is called the length of S. So what is a weighted zero-sum sequence? The let S be a sequence over G0. We choose the gamma to be a subset of the endomorphism group of G. So we say S is a zero-sum sequence if the sum of all the terms of S equals 0. We say S is a gamma-weighted zero-sum sequence if we can choose weight gamma from the capital gamma such that the gamma 1 G1 plus up to gamma L GL, the sum of this is 0. So we denote this BG0 to be the monoid of all the zero-sum sequences over G0, and let the B sub gamma G0 the monoid of gamma-weighted zero-sum sequences over G0. So it is natural to say that the B sub gamma G0 is a subset of Fg0. Here the Fg0 is the set of all the sequences over G0. And to see that Bg0 is a subset of B gamma G0, we see that if S is a zero-sum sequence, and since the weight is chosen from endomorphism group gamma, and if we have one gamma, it's an endomorphism, so it maps 0 to 0. So it maps the zero-sum sequences. It maps the sum of all the terms. If the sum of terms is 0, then the gamma maps the sum of terms to 0. So it is a gamma-weighted zero-sum sequence. So all the zero-sum sequences are still gamma-weighted zero-sum sequences. In particular, if we choose gamma to be the identity, it has only one element, that is identity map, then the B sub gamma G0 is BG0. And we see some examples. First, if gamma is a singleton, where gamma is an endomorphism, so if S is a gamma-weighted zero-sum sequence, if and only if the sum of since the weight has singleton, so we can only choose the weight to be gamma. So that gamma G1, the sum of gamma G1 up to gamma GL is 0. If and if this gamma, the sum of all the terms sigma S, I mean gamma sigma S is 0. So which means that if S is a gamma-weighted zero-sum sequence, if and only if the sigma S is in the kernel of gamma, so when the B sub gamma G is all the sequences such as the sum of S is in the kernel of gamma. In particular, if this gamma is an automorphism, so the kernel of gamma is trivial, and hence the B sub gamma G is a BG, which means all the gamma weighted zero-sum sequences are just the zero-sum sequences. If gamma is 0, which means gamma maps all the element of G to 0, then the kernel of gamma is G, and hence all the sequences are gamma weighted zero-sum sequences. So the B sub gamma G equals FG. Now we just see a special gamma. That means the identity map, the minus of the identity map is in gamma. Then the S to the power 2 is for only sequence S to the power 2 is a gamma weighted zero-sum sequence. Since we can S to the power 2, so for each term G, we can map this term G to G and maps another one to minus G. So it is so the sum is 0. And if the gamma is order automorphism group, and we choose the G to be an elementary 3 group, we see that for only 2 non-zero elements, G1 and G2, there is a automorphism gamma such that gamma G1 equals G2. Now we can see then this G1, now if we can choose a weight gamma, which maps this G1 to minus of G2, and choose another gamma maps G2 to D2, then this G1, G2 is a gamma weighted zero-sum sequence. And if we have 3 non-zero elements, G1, G2, G3, so we can choose the weight gamma, we map G1 to G1, and G2 to G1, and G3 is also to G1. Since we are in the elementary 3 group, this G1, G2, G3 is also gamma weighted zero-sum sequence. Means that the B sub gamma G is the sequence that it has at least 2 terms that is not 0. Okay, next we see the motivation. The weighted zero-sum problems over finite orbital groups were introduced by Krull and others. And the idea to use homomorphism as weights is due to Yuan and Zheng. The focus of early work was on combinatorial aspects of the theory, for example, on weighted analogs of the Davenport constant or the weighted Aldous-Ginsburg-Leaf constant and others. The arithmetic of a Krull monoid or of a Krull monoid with class group G is closely connected with the arithmetic of associated monoid of zero-sum sequences over G, which means we want to study the arithmetic of a Krull monoid or Krull domain, where we can study the arithmetic properties of the monoid of zero-sum sequences over a finite orbital group. So this is done by a transfer homomorphisms, and we can build a transfer homomorphisms from non-monoid of Galois invariant orders in algebraic number fields or from monoid of positive integers to the monoid of weighted zero-sum sequences. Since we can build such a transfer homomorphism, so if we want to study the arithmetic of non-monoid or the monoid of positive integers, then we can just study the arithmetic of the monoid of weighted zero-sum sequences. The arithmetic investigations of monoid of weighted zero-sum sequences are initiated by Schmidt and others. Okay, next we see the algebraic properties first, and the algebraic properties, and we are interested in the semi-normal, root closed, and completely closed. We see a monoid H here means a multiplicative, commutative, cancellative semigroup with the identity element. We denote by QH, the quotient group of H. Here we define the H prime to be those set X in QH such that there is a N such that x to the power n is in H for wall that n is larger than or equal to the capital N. This is called the semi-normalization of H. We will be the type of H to be the set of wall X in QH such that there exists some primitive integer n such that x to the power n is in H. This is called the root closure of H. Where the head of H is the set of all rows X such that there is some C in H such that C times x to the power n is H for all the primitive integers. This is called the complete integral closure of H. By definition, we can see that H is a subset of H prime, which is a subset of type of H. The head of H is subset of QH. So when we say H is semi-normal if H equals H prime. H is root closed if H equals the type of H, and H is said to be completely integrally closed if H equals head of H. Next, we are interested in properties of Krull, weakly Krull, and transfer Krull. A monoid H is said to be a weakly Krull monoid if the intersection of all the localization of H and prime minimal ideals P in H and all the minimal prime ideals P contains a fixed element is finite. The number of the minimal prime ideals contain a fixed element is finite. We say H is a Krull monoid if H is weakly Krull and the localization of H and a prime and a minimal prime ideal is a discrete value H monoid for. Or equivalently, there is a divisor homomorphism phi from H to D. Here, D is a Fair-Bender monoid. Here, the divisor homomorphism that is H if A divide B in H, if and only if phi A divide phi B in D. We say H is a transfer Krull monoid if there is a transfer homomorphisms theta from H to B. Here B is a Krull monoid. Here the transfer homomorphism, which means we can lift factorizations of B to H. If we have such a transfer homomorphism, we can study the factorizations of H. We can just study the factorizations of B. Okay, we see that if the Krull implies that completely integrally closed, and Krull also implies the weakly Krull and transfer Krull, and it is completely integrally closed, then it is root closed. If it is root closed, and it's semi-normal. So we want to study those properties. First, if the monoid of weighted zero-sum sequences, we say if it's root closed, when it is root closed, we have this theorem. I mean, let G be a Fairbairn group, gamma to be a subset, such that the identity map and the matrix of the identity map is in gamma, and the following are equivalent. And B gamma G is root closed if and only if this B gamma G is Krull. If and only if B gamma G is transfer Krull. If and only if B gamma G is weakly Krull. If and only if G is an elementary 2 group, and the gamma has only these 2 elements, and the B sub gamma G is exactly BG. So we can see that here that if B sub gamma G is root closed, it is just that is just BG. So that the root closed seems the property is too strong, such that no other gamma weighted zero-sum sequences or wall zero-sum sequences. So we want to consider a weaker property, which means when B sub gamma G is semi-normal. Here we see some name first. We consider here the gamma is the same, and if B sub gamma G is semi-normal, the exponent of G is a power of 2. To see this, we assume to the contrary that if there exists an element G such that the order of G is what? The order is what? I mean, just suppose the order of G is n, then G to the power n. This is a zero-sum sequence. Then it is a gamma-weighted zero-sum sequence. And the G to the power 2, since here the minus identity map is in gamma, so G to the power 2 is still a gamma-weighted zero-sum sequence. Then by definition of the semi-normal, that means that G to the power k for all k is not equal to m, and G to the power k is in is a gamma-weighted zero-sum sequence. So this G, the element G, is in the semi-normality of the B sub gamma G, but the G is not gamma-weighted zero-sum sequence. We get a contradiction. And here, if the gamma has only 2 elements, we write it in that B sub plus minus G. So if the B sub plus minus G, if this is semi-normal, then exponent of G divide 4. To see this, we also assume to the contrary, that the exponent of G do not divide 4, And since from the first item, we see that exponent of G is a power of 2, and the exponent does not divide 4, then there exists an element G such that the order of G is 8. So we consider this sequence S, which has 2 terms, it's G and 5G. Then S to the power S to the 2, this is a plus minus weighted zero-sum sequence. And we consider S to the power 3, and which can be written as a product of G to the power 3 and 5G. This is a zero-sum sequence, and it's a plus minus weighted zero-sum sequence. And 5G to the power 2 is still a plus minus weighted zero-sum sequence. So S to the power 2 and S to the power 3 are all plus minus weighted zero-sum sequences. So S is in the semi-normality of B sub plus minus G, but S here is G and 5G. This is not plus minus weighted zero-sum sequence. We get a contradiction. Okay, from this, we consider 2 cases. If the B sub plus minus gamma G is semi-normal, if and only if exponent of G divides 4. And if this holds, we can get the completely great closure of B sub plus minus G is all those sequences such that the sum of the sequence is in 2.G. And we consider another case that if we choose gamma to be the group or the automorphisms, then the B sub gamma G is semi-normal if and only if G is isomorphic to copies of those copies of Stickney groups, and where for each copy the order of each Stickney group is different. That means it is isomorphic to this 2 to the power 1, and here all the TI are different. And if this holds, we can also get the complete integrated closure of the B sub gamma G, which is all those sequences such that the here NS is even, the NS is, which means the number of the terms that has a order exponent of G, and means it's the number of terms and exponent of G is even. And here we see we want to talk about when the B sub gamma G is semi-normal. Here from these 2 cases, we consider 2 extremity cases. I mean, first, gamma chose to be minimal choice, and means we chose gamma to be the identity map and the minus identity map. From this case, the B sub plus minus G is semi-normal if an exponent of G divides 4. And if we choose gamma to be the maximal possibility, which means the gamma is the automorphism of G. And we see that the 2 cases do not include each other. That means here that you choose C4 plus C4, it is for B plus minus G. This is semi-normal, but for the gamma chooses all the automorphisms, and it is not semi-normal. Okay, next we see some arithmetic properties of B plus minus G, and here with let G to be a finite abelian group, let S be a sequence over G. We say S is zero-sum free if S has no non-trivial zero-sum subsequences. We denote by the S star G to be the set of all zero-sum free sequences. We say S is a minimal zero-sum sequence. If S is zero-sum and S cannot be written as a product of two non-trivial zero-sum sequences. We say S is plus minus weighted zero-sum free if S has no non-trivial plus minus weighted zero-sum subsequences. We say S is a minimal plus minus weighted zero-sum sequence if S is plus minus weighted zero-sum sequence and S cannot be written as a product of two non-trivial plus minus weighted zero-sum sequence. Here are some examples. Let G be an element of order n. We can see that G to the power n minus 1 is zero-sum free, and G to the power of n minus 1 is not plus minus weighted zero-sum free. Okay, since I spent too much time in that section, so we skip this part maybe. Okay, next we give some definition of the Davenport constant. We denote that dg is the maximum length of all the minimal zero-sum sequence, and divide small dg is the maximum length of all the zero-sum free sequences. And similarly, we can denote d plus minus g to be the maximum length of all the minimal plus minus zero-sum sequences, and the small d plus minus g to be the maximum length of all the plus minus zero-sum free sequences. So, and we let G to be the direct product of 16 groups. Here we divide this N1 divide N2 divide NR, and let G to be minimal such that NT is even. So we can define this D star G and this D star plus minus G in this way. So we obtain that here we call it maybe the natural Davenport constant. The natural Davenport constant, the D star G is a lower bound, and exponent of G times 1 plus log G, the order of G over exponent of G is the upper bound. This is a classical result. And Hickel, Greenquist, and Shun, they proved that for the small Davenport constant D plus minus G, it has a lower bound and upper bound in this form. And Schmidt and others recently they proved the natural plus minus Davenport constant also have this bound by the Davenport constant of G and bound by this invariant we defined before. And they also proved if the order of G is odd, then the large plus minus Davenport constant equals the Davenport constant of G. So if G is cyclic, so if G is cyclic, or the lower bound meets the upper bound, we obtain that the Davenport constant of G is a order of G, and the small plus minus Davenport constant of G is just the flow of the log to the order of G. And the large plus minus Davenport constant of G is, if the order of G is odd, then it is order of G. If the order of G is even, it is 1 plus the order of G over 2. And we want to talk about the case elasticities. Here for every K, we denote about the row K, the maximum integer L, such that there exists minimal zero-sum sequences U1 up to UK, V1 up to VL over G, such that the product of UI equals the product of VGS. Similarly, we can define as row K be plus minus G. And it's easier to see by this definition, this row, if we choose, choose this row K1H plus row K2H, which is bounded by row sub K1 plus K2. Here we want to skip this about the properties, and we see that it's easier to see that the case elasticity of BG is bounded by K times DG over 2. And if the K is even, we know it, that means the 2K's elasticity is just the K times dg, and for the plus matter weighted sequence, we have a similar result. And the difficulty is we want to start if the K is odd. I mean, here we talk about when it is 2K plus 1. If this is a cyclic group, Gao and Godinger, they proved that the 2K plus 1's elasticity is just K times dg plus 1. And in 2016, we put if G is a non-cyclic group, but dg equals d star G, then the 2K plus 1's elasticity is floor of the 2K plus 1 times dg over 2. Here K is for all large K. And recently we proved that this G is a Fetter-Benning group of odd order. Here, if the G has odd order, we know that the large plus minus large double constant is the double constant, the large double constant of G. So here, if dg equals d star G, we obtain that the 2K plus 1's elasticity of the monoid of plus minus weighted sequence is obtained the upper bound. Here, to compare two results, we see here for all K is for K it holds for all positive integers, and this is hold for all large enough K, and all those proofs are highly depend on the structure of zero-sum sequences of maximal length. So here we divide this dg equals d star G. And okay, thank you for your attention.
Thank you. Are there any questions for our speaker? We have a second or two. Let me thank you again for your very nice talk.